Good day once again, everyone, and we meet yet again. And once again, we're going to, as we're preparing for the prelims, we're going to be looking at multiple choice questions this time based on paper two. So if you haven't subscribed, please just do the right thing and please just give this lesson a thumbs up if you like it. Okay, and let's get right into it as you prepare for those prelims or for your final exams. Okay, so I want to do paper two on question on multiple choice, and I'm taking the 2021 May June paper. All right, and you'll see there are quite some interesting questions there. Okay, let's get right into it. All right, so the first one says which one of the following compounds has a hydrogen bond between molecules? Okay, as you would know, hydrogen bond is found in organic compounds, right, between alcohols. Okay, they've got that hydroxide group, and then also carboxylic acids. So let's see which one would actually qualify there. So that would be pentanoic acid. So obviously the answer here should be C, right? And then the second question says, to which homologous series does a compound with a molecular formula C6H12 and O2 belong? Okay, so as you would know, there are only two compounds in organic chemistry that have two oxygens. So that was my first clue, right? So this compound should have two oxygens. So it could either be an ester, or it could be a carboxylic acid, right? So let's look at those. So the only ones there that would be carboxylic acids. So the answer should be D. They say which functional groups are involved in the formation of esters. Now, you remember, ladies and gents, that esters are formed when a carboxylic acid reacts with an alcohol, right? Okay, so remember, in the presence of an acid, um, so they say which functional groups are involved there. So it should be the hydroxyl ion, which is from the alcohol, as well as the carboxyl ion, which is from the carboxylic acid, right? And in this case, so the answer there should be C. Okay. Right, and I saw what should be a very interesting question. People have been asking me about the common ion effect, and this would be quite a good question to kind of explore that. Okay, so they say the equation below represents a reaction at equilibrium. So essentially, you've got the chromium ion, or in this case, the dichromate ion, in this case, right, reacting with an H plus there. This guy is yellow, okay, reacts with an H plus, forms that ion, okay, and water, and which is this guy is orange. So you would naturally expect that at equilibrium this solution would kind of turn yellow. I don't know what's a mixture of orange and yellow, something in between that, right? So when I favor the forward reaction, please, I want you to listen to me carefully, ladies and gents. So when I favor the forward reaction, obviously it means that I would therefore form more products, and as a result, my solution should turn a deeper orange color. Okay. Um, so in this case, that's because of the presence of that ion, right? And if I reverse that reaction, or if I do something to the conditions at equilibrium that causes the reverse reaction to be favored, then this solution would kind of turn yellowy in color. Okay, right. So they are asking us the following question: which one of the following will change rather the color of the mixture from yellow to orange? Now, in essence, what they are asking us is which change would favor the forward reaction. Now let's look at the changes that they've given. Okay, so they say that the addition of sodium hydroxide pellets. All right. Now you may ask yourself, okay, what does sodium hydroxide have to do with this? Right. Now remember, the moment I add sodium hydroxide, remember that sodium hydroxide has got those hydroxide ions, OH minus, right? So you've got the presence of those hydronium ions, and of course they always want to neutralize each other. So therefore it means when you add sodium hydroxide, the OH minus ions start taking away the H plus ions. Okay, they react with those H plus ions to form water, right? So in effect, what they are simply doing here by adding sodium hydroxide, they are actually reducing the H plus ions, okay? Because obviously they will, they will react with the hydroxide ions, right? So as a result, which reaction will be favored if I reduce the H plus ions, right? So equilibrium shifts to the left to try and replace the hydronium ions that would have been taken away, and as a result, it would turn more yellow, okay? So that wouldn't be an option, right? And then they say addition of concentrated hydrochloric acid. Now, I want you to please note, the moment I add hydrochloric acid, remember, now this is what we call the common ion effect, right? So remember that hydrochloric acid, okay, has got, so it's got those so HCl, okay, has got H plus ions as well as Cl minus ions, right? So by actually putting hydrochloric acid, it means I am now increasing the presence of my hydronium ions, right? My H plus ions. So in this case, it means you are now adding more hydronium ions. It will definitely, equilibrium will now be shifted to the left, to the right rather, to try and use up those hydronium ions. So in this case, my solution should turn orange, okay? So would move from yellow to orange. So it looks like B is the option, but let's look at the next one. Okay, they say increase in pressure at constant temperature. Pressure is not really going to have to change anything there. The reason for that is that none of those substances are in gaseous phase. Okay, so remember, pressure will affect substances that are in gaseous phase, that are gases, right? So in this case, pressure has got nothing to do with it. So both C and D are out of the question. So in this case, obviously, we are left with B. Okay, right. Let's go to the very next one. Okay, quickly there. Right. So they give us that reaction. Now, if you haven't looked at it as yet, there's a video that I made on chemical equilibrium. No, not chemical equilibrium, rather, rates of reactions, okay, wherein I go through these kind of graphs. So please just have a look at that if you haven't as yet, so that you can be able to answer this question with ease. Right, let's go into it quickly. So they say to us, so we're given, they say, consider the potential energy for the reaction shown below. Now, when I look at the graph at face value, right, this tells me this must be an endothermic reaction. If you remember, for an endothermic reaction, I would know it means that the forward reaction rather is endothermic, because I know I start with a lower energy, right? So the energy of the reactants would be lower and the energy of the products would be higher, right? So it would signify that the activation energy for the forward reaction is much greater, right? Right, of course, if you don't know what I'm talking about, obviously it means that you haven't watched that video. Just go and do that quickly for yourself. Right, now they say to us the activation energy for the forward reaction, okay, in terms of PQ and R is, now I want you to please note, okay, let me just draw an equivalent of this graph over here so that I can show you. Okay, I'm avoiding having to draw onto the question paper itself. Okay, so there's P, there is Q, there's R, and there's Q. So Q is what we call the activated complex, right? So in this case, I know that Q would represent the activation complex. So this would be the energy of the products, okay? So or rather let's say H product, and obviously this one would be the H of the reactants. Okay, now for me to calculate the activation energy for the forward reaction, you always start with the energy of the reactants up until the activation complex. So it's that it's the difference between those two values there. Okay, so they said the activation energy for the forward reaction, so in this case it must be from P to Q. Okay, so there's our answer there. That would be Q minus P. So this value minus that value gives us the activation energy for the forward reaction. And then just as a matter of interest, if I wanted the activation energy for the reverse reaction, this would now be Q minus R. Okay, and remember delta H. Okay, our change in enthalpy there. In this case, this would be R, okay, H of the products minus that of the reactants, so it would be R minus P. But we are interested in the question that we are being asked, so in this case this would be Q minus P. Okay, right, we are moving very swiftly. Okay, they say a reactant, okay, the next one, they say a reactant reaches equilibrium in a closed container according to the following balanced equation. Okay, so just some things to note there. They said delta H is less than 0, right? So which means this is an exothermic reaction. It means that delta H is less than 0. You know, if for those of you who haven't watched the video on equilibrium, okay, so I said, how will you know? I always use the Pac-Man thing, right? So I said, just imagine this was a Pac-Man. Okay, I draw some teeth onto my Pac-Man. So my Pac-Man is facing that way. So it means that heat must be on the right-hand side. Okay, so it means when you write down that reaction, it's going to be 3H2, okay, gas plus nitrogen, okay, and that would be 2NH3. But what you simply do is, okay, I'm going to write plus heat over there. Okay, it means that heat is given off. All right, so when this reaction takes place, heat is also a product. Okay, right, so they say which one of the following changes will increase the value of the equilibrium constant. Now please, I want you to remember, ladies and gents, it's only temperature that changes the value of the equilibrium constant. So in this case, when I look at those, they say removing, that's heating the container. Okay, now we want the equilibrium constant to increase, right? So in this case, A and D are disqualified because they have nothing to do with temperature, right? Now look at this. If we heat the reaction, I want you to please note, if we heat this reaction, it means that we are increasing heat, which is on the right hand side. Okay, right? So remember, if I increase something that's on the right hand side, I favor the reverse reaction. Okay, because now equilibrium says I want to use up that heat there, so the reverse reaction is favored. Okay, so as a result, it means that NH3 will decrease because we will now be using it. Okay, it means that nitrogen would increase as well as hydrogen would increase. And if you think about equilibrium constant, Kc calculation, it's always going to be the molar concentration of your product. So that would be NH3, right, squared divided by nitrogen, okay, and hydrogen, the molar concentration of hydrogen. Remember, this should be to the power 3. Now, the only way that I can increase the Kc value, it's if I have a reaction that will increase what is on my numerator. Think about it. When my numerator increases, then it means that my the entire fraction will increase, right? So in this case, I want my NH3, the molar concentration of NH3 to increase, and obviously these ones to decrease. So in this case, it means that heating the reaction, heating the container is really not going to cut it. Why? Because it will now decrease the NH3 amount there, right? So cooling the container, okay, now that one makes sense, because if I cool the container, it means I'm decreasing the temperature. Equilibrium says, look, I want to try and replace the heat that was taken off. All right, so as a result, the forward reaction is favored, NH3 increases. So our answer there should be C. Okay, right, as we are moving very swiftly along. Okay, right, so let's take the next question. So if you look at this one here, they say to us we are given sulfuric acid. Okay, sorry. So sulfuric acid ionizes in water according to the following equation. Okay, so you look at that there. So there's H2SO4 and it's reacting with water, right? And H3O plus is formed and HSO4 minus. Now, if you note this, H2SO4 gave away its H plus, and as a result became HSO4 minus, right? So this guy must have been the acid. So water in this case acted as a base. Why? Because it accepted an H plus. Okay, that's according to the Lowry-Bronsted theory, right? So it accepted an H plus, so it's a base. Okay, and as a result, when we take the reverse reaction of that, it means that H3O plus would be the acid. Why? Because it would give away the H plus and thus form H2O, and HSO4 minus would be the base. It accepts and becomes H2SO4, right? Okay, let's go to the next question, the next reaction. Now, HSO4 minus is okay, reacts with H2O again, right? So this is our acid, because now it gives away the H plus and becomes SO4 minus, SO4 2 minus rather, right? And as a result, H2O is formed, H3O plus rather is formed, the hydronium ion there. Okay, so they say consider the following statements regarding the ionization above. Okay, they say H2O acts as a base in both reactions. Okay, I absolutely agree with that. In both reactions, it accepted an H plus and became H3O plus. Okay, and then they say HSO4 minus acts as an ampholyte. Okay, I would totally agree with that, because remember, in this case, for the reverse reaction, HSO4 minus acted as a base, right? And it became H2SO4. It accepted a proton, right, and became H2SO4. But if you look at this reaction here, reaction 2, if I may call it that, HSO4 gave away an H plus, so it acted as an acid here. So yes, it is an ampholyte. Okay, and then the last one says SO4 2 minus is the conjugate base of H2SO4. Now remember, if you remember, for those of you who watched the video on acids and bases, I showed you how to get conjugate bases, right? So in this case, the conjugate would always be something that almost looks the same, with just one H plus as a difference. Okay, so if I look at that, HSO4 minus is the conjugate of H2SO4. Here, HSO4 minus is the, or SO4 2 minus is the conjugate of SO4 minus. Okay, so in this case, I would totally disregard the third statement. It is untrue. Okay, so as a result, the ones that are true would be statement 1 and statement 2. Okay, so our answer there should be B. All right, and then the next one, they now say which one of the following reactions, when used in a voltaic cell, so that's the galvanic cell, right, will give a positive reading in the voltmeter. Okay, now perhaps what I will do is, let me just take a standard reduction table so that I can show you how to do that one. Okay, let's pull one right here. Okay, so there'll be no other way, or I suppose there are other ways in which you can try to do this quicker, but I'm going to show you from the standard reduction table. So let's take the first one as an example. If I took magnesium, okay, and as well as zinc, okay, let's find them quickly onto the standard reduction table. So what I would do to check which one is would give me a positive value, okay, I would go to my number line method, right? Let me check if so I look at zinc. Zinc is minus 0.76 and magnesium is minus 2.36. So which one has a smaller value? Okay, in my number line method, for those of you who haven't checked it, please just see the videos that I've made on that. So this would be magnesium, okay, and this would be zinc. Okay, remember in the number line you always start with a smaller number to the bigger number. Okay, so zinc would be minus 0.76. So both of them are negative in this case, but obviously this one is a bigger number than minus 2.36. So now what this tells you, now please I want you to note this, if this is going to be a galvanic cell, if I'm going to get a positive answer, so in my in my method I always say, okay, it's as easy as ABC, right? So it means that this one should be the anode and this one should be the cathode, right? And what happens between the anode and the cathode? Okay, it gives away electrons, isn't it? Okay, so in this case, please I want you to note, so it simply means that in this galvanic cell, all right, if it's to be a galvanic cell with a positive EMF, magnesium must be the anode. So it means that magnesium must give away the electrons, right? And I said to you, once you identify which one is the anode, remember, you take the reaction of the anode from your standard reduction table, okay, and you write it the other way round. Okay, so in this case it means that for this to be a galvanic cell, magnesium has to undergo oxidation, magnesium 2 plus, okay, by giving away 2 electrons. And if you note there, that is not the case. Magnesium actually undergoes reduction, okay, and becomes Mg, whereas here, in order for it to be a positive galvanic cell with zinc, magnesium must undergo oxidation. So A is not an option. Okay, so I'm kind of showing you how to do that, and you'll do that for all the others. Okay, if you take the one between copper and silver, okay, again, so look at that, copper and silver. Copper is 0.34, okay, and silver is 0.8. So 0.34 and 0.8. So it means that copper would tend to undergo oxidation, okay, right? So it gives away electrons. So it means that copper should be able to undergo oxidation. So copper must undergo oxidation by giving away electrons. Is that the case there? All right, so copper becomes copper 2 plus, and in this case that is what we find. So I think that B is correct. All right, you can verify the others. I was just showing you how to go about answering that question. So copper does undergo oxidation there, and silver does undergo reduction in that case. So as a result, it means that should give me a positive EMF value. Okay, right. So, right, let's go swiftly along. So, which one of the following statements is correct for an electrolytic cell? Okay, they say the anode is positive. Now, please remember, ladies and gents, for an electrolytic cell, okay, please, I want you to always note, in this case, we said the anode, okay, again, if you have not watched videos on the electrolytic cell, right, we said the anode is the positive side of the cell, okay. Remember, in the galvanic cell, we found that the anode is negative. And why is that? Because that is where electrons are manufactured. Okay. They always, between the bread, between the bakery and the home, where are you likely to find more bread? In the bakery, isn't it? So in this case, because electrons are made at the anode for the galvanic cell, you find more electrons on the anode, because it's the one that's giving away electrons, isn't it? So as a result, the anode is negative for the galvanic cell. However, for the electrolytic cell, it's actually the other way around. Okay, so the anode is positive, okay, and the cathode is negative. That's where reduction takes place. Okay, right. So I see there I would go with A. All right, but let's look at why the others are not correct. They say the cathode is positive. That is not true. Okay, remember I just said the cathode is negative there. Okay, oxidation takes place at the cathode. No, remember, whether galvanic or electrolytic cell, oxidation always takes place at the anode. And they say reduction takes place at the anode. Of course, that is not true either. Okay, so in this case, that is also not true. All right, now the very last one, and I would know that for those of you who are preparing, you know that this part won't necessarily form part of your examination. However, I will answer the question nonetheless. They say, which one of the following shows the industrial process in which ammonia is a reactant and a product, respectively? Okay, so where it is a reactant, all right, that would be the Oswald process. Okay, that's the catalytic oxidation of ammonia. That's the first one. And then where it is a product, it's the Haber process or the Haber process. I don't know how you want to pronounce it. It's up to you. Okay, so let's see. So the correct answer there should be B. Okay, all right. So ladies and gents, we've come to the end of this multiple choice section. And I hope that you will appreciate that as you prepare for the exams. Remember, the thing about multiple choice is that you always need to make sure that you do your absolute best. Now, if at all you find that it is difficult to do at first, rather start with the long questions and answer the multiple choice section later, okay, afterwards. But just make sure that you are always cognizant of time, okay? Otherwise, thank you so much for listening, ladies and gents, and I'll see you again next time. For those of you who haven't subscribed, please just make sure that you are part of the family, okay? And good luck for all your exams. Sharp, sharp.